All right, in this lesson, we're going to do a deep dive on the search for extraterrestrial intelligence. So, we're going to be assuming from now on in this lesson that there is extraterrestrial intelligence. There are alien civilizations out there that are trying to communicate, maybe sending messages out into space or looking to receive them. All right, and so we're putting on the hat of someone who has that frame of view, and we're asking the question, which becomes an interesting question: how would you communicate with them? Right? How would you listen for messages from them? That's kind of what we're getting at. Now, before we go there, it's worth spending just a quick word on how we are likely to detect life in the universe. If there is any kind of life in the universe, not just intelligent, what would it look like? And this is what it would look like. So if we take this more I would call it scientific approach of like discovering planets, looking at their atmospheres, what we'd eventually hope to see is a graph that looks something like this. All right, this is a spectrum of a planet like the Earth. So if we could observe the Earth from a really long ways away, what would the spectrum of the Earth look like? And could we detect the presence of life in that spectrum? Right? So again, a spectrum gives all these kind of fingerprints of the different chemicals that you find somewhere. And there are certain chemicals in Earth's atmosphere that are caused or related to life. For example, water, H2O, which has these significant features, oxygen, O2, ozone, O3, we have carbon dioxide, and we have nitrous oxide, I think that's what that, N2O, I don't actually know what that is, and then CH4 is ammonia. All right, so these are chemical signatures. We call them biosignatures because they're chemical signatures that are connected to biological systems. So these are the kinds of graphs that scientists would someday point to say there may be grass on that planet, or there's maybe, some form of life. But there are also geological causes for a lot of these chemical tracers. So it will often be probably inconclusive for the foreseeable future. So that's where we get to taking this step. So this is kind of the more, what would you say, the more scientific approach, right? When we talk about SETI and the search for extraterrestrial intelligence, what we're talking about is sort of saying, like, let's just bag that. Let's say there are aliens out there and they're sending us signals. Because, man, if we detected a signal that said, like a radio message, and it said, hey, how's it going? Well, then we don't need to worry about all these graphs. We just be like, we know they're out there, right? We found them, right? And so that's what the search is about. Now, SETI's been around probably since the 60s at least, and there have been a couple ways that this kind of idea of communication with intelligent civilizations has interfaced with more traditional mainstream science, right? And we've seen a couple examples of that. One was the Golden Record, right? The Voyager Golden Record was a case where we recorded all these images representing space in the thought that, hey, if someday someone finds this spacecraft, this Voyager spacecraft that's flying through space, they could understand the people that it came from. Prior to that, though, was a mission called Pioneer 10. And Pioneer 10 was actually the very first space mission that was launched, which would exit our solar system and go on forever. And so folks like Carl Sagan said, we need to put something on here, some kind of message in the bottle, so that if any alien civilization were to find this, they could learn something about the creatures who sent it. And so what they created was a plaque that went on Pioneer 10. And this is what that plaque looks like. All right? So you can get your giggles out now, okay? They do show like a cartoon drawing. Nothing that you didn't see in sex ed probably. So, but here's the idea. It shows at the top, it shows like a basic understanding of the hydrogen atom. And then this map here on the left shows a pulsar map, which is meant to show like the location of the sun relative to these pulsars. So again, it's supposed to be a map. And then on the bottom, you have a map of our solar system, which is meant to show the trajectory of the Pioneer spacecraft. And you have the Pioneer spacecraft behind the image of a man and a woman. Now, this plaque caused like all sorts of controversy, right? Because this went from like a NASA sanctioned mission. You've got two naked people. It's like, what are you doing? And then more than that, though, some feminists believed that the woman was a more subdued body language, and why is it that only the man is saying hello? Like there was there was a lot of controversy around that, which is why you see the Golden Record was a much more thoughtful and ecumenical, like it included many different cultures, even the people look like they're kind of like Americans. They don't seem representative of people of other nations. And so the Golden Record was a much more thought out and political process, shall we say. But now those are just small examples of literally like a message in a bottle, like this thing you're just throwing into the ocean thinking, hope someone sees that someday. But those spacecraft are, even at the insane speeds they're traveling, are really not going to go very far, very fast. The thought that they'll ever encounter an intelligent civilization, if one exists somewhere, is extremely low. And so that's where we turn to other methods of communication, right? We don't send mail to each other to communicate. We send electronic messages. We send cell phone signals. We communicate faster than that, even here on Earth. And so we turn to the electromagnetic spectrum, right? Because nothing can travel faster than light. So let's use light in all the different forms, whether that's visible, radio, whatever it is, to communicate with any civilizations that might be out there. At least that's how the logic goes. Now, if you're going to choose a part of the spectrum to be searching in, you've got some constraints on you, right? So say you want to be broadcasting a signal for someone else to listen in on, or even if you want to listen on a signal. If you're looking at a certain part of the spectrum like gamma rays and X-rays, you've got some problems over here because these are extremely high energy forms of light. So they take a lot of energy to make, and they're dangerous to work with, right? So we don't want these huge like gamma ray dishes like sending gamma rays out into space. Okay, it would be extremely expensive and dangerous. And then you get into things like ultraviolet. There you get some issues that our atmosphere is not even transparent to ultraviolet radiation. So the light won't even go through our own atmosphere. So how are you going to send or observe signals? It wouldn't even go through the atmosphere. Okay, and you get into the infrared, and we're getting better, but again, a lot of the infrared is absorbed by the spectrum, by the Earth's atmosphere. As you get to longer wavelengths, these are really good. Microwaves and radio waves in particular are really good because they're low energy, so they don't take much energy to produce. They travel through things, right? Just like infrared can go through dust, radio can go through anything, right? It can go in and around buildings, and it can go through the atmosphere, and it can go through interstellar dust. So it travels very well throughout the universe. It also so happens that a portion of the radio spectrum, there's really not much in the universe that's giving off that kind of light. So there's some natural pressures that say we should be looking in the radio part of the spectrum and using the radio part of the spectrum. But even if you've narrowed it down to the radio, I believe I've showed you this before, right? You've still got to tune the radio to just the right frequency, right? Like if you're using an old-timey radio, okay, or even one of the digital ones, and you're not on exactly the right station, you're not going to get the signal. You've got to, so where are you going to tune it is a real question. And if you're going to be looking at a real range, then you have to be recording and analyzing them all. So this is a real problem. So check this out. This is a map, and this is what I wonder if I've showed you before. This is a map of the United States frequency allocations for the radio spectrum. So now we've reduced ourselves to just the radio part of the spectrum, but for communications and all different purposes, the federal government actually breaks up that radio spectrum into all these tiny pieces and gives them different uses. So you can see here on the left, some of them are for navigation, for mobile phones, for your boat communication, for amateur radio, for television, for radio like radio music, for space research. Some is reserved for space operations, like for people on orbit. All right, so it's all broken up so that everyone stays in their own area, so they aren't like interfering with each other. So you'd have to pick what part of this spectrum are you going to try to observe in, right? And in fact, one portion that's reserved for radio astronomy is on here, and it's a very specific part. I wonder if I'll even be able to see it. It's reserved for a very specific part because you can observe spectrum of hydrogen atoms in the radio part of the spectrum. So this is a real challenge. And now on top of that is this question of bandwidth. Okay, so when you think about bandwidth, if you've heard that word, you think about like how quickly your internet works. But bandwidth is like how many frequencies is the signal spread over. So for example, when you tune the radio, it has to be on, for example, 92.1, right? FM. That's the signal that you're tied to. And that has a certain bandwidth that if you could be off by just a fraction, you might still hear the signal. But if you go too far off of that core value, you're going to lose the signal. Well, you could imagine an alien civilization that's sending a signal and it's on a very narrow bandwidth. So you have to get exactly the right signal to get the message. Or it could be sending it spread over a really broad bandwidth. And if you're observing this little part, you might actually only be getting a tiny portion of the message. Such a tiny portion that you don't even recognize that it is in fact a message, right? Because you have to be looking over this full range to even know that it's a message. So there's all kinds of challenges associated with like, where do you look? Like, where in the sky do you look? What wavelength of light do you look at? What specific bandwidth are you looking at? And these are all like super significant challenges. Oh, I'm overwhelmed just thinking about it. What SETI has done is to say, we need to at least be listening. We need to at least be looking, because maybe, Drake's equation, maybe there's 180,000 intelligent civilizations in our galaxy and they're all beaming messages. And if we're not even listening, we're missing out on the most important information that's being shared in the whole universe, right? And so they've been listening for like 40 years and they haven't heard anything yet. But as we've said, it's an incredibly difficult thing. So there's this tension, right? If there are tons of these intelligent civilizations, why haven't we heard from them yet? We'll explore that more next. But if they are there, how do we hear them? How do we tune in and find them? Okay, so what I'd like to do, let's see, should I share? Let me share. Should I share? Let me go to SETI first. So here's SETI's website, the SETI Institute. Okay, and you can see that over time, while I think it's fair to say that when they first began, SETI was very fringe. Okay, increasingly they've become more scientific and more accepted as their research has extended to astrobiology and other areas beyond just the search for intelligent civilizations. But that certainly is their core mission. You can see as you look at SETI research, we have SETI 101. Let's just take a look at what that is. This talks about the history of the organization. There's Frank Drake. Okay, a history of it. He did independence. Let's see, 1960s, he conducted the first microwave radio search for signals from other solar systems. So this started in the 60s. In the 1960s, the Soviet Union dominated SETI, and it frequently adopted bold strategies. Very interesting. Okay, so there's a ton to explore here, but you can see some of the research. One of the telescopes they use. So one of the challenges, right, with SETI is getting telescope time, right? How do you convince a panel of astronomers that they should give you time on these extremely expensive telescopes to look for aliens, right? So one of the ways they've approached to do that, they do get some time, but one approach is by building your own telescope. And so a very wealthy donor, Paul Allen from Microsoft, put up a ton of money to make what's called the Allen Telescope Array. So this is a collection of microwave and radio telescopes that will continuously be searching for intelligent life in the universe, signals from alien life. All right, I'm wondering if it's actually, yeah. Okay, so it is currently functioning and collecting data, and that's probably their primary source of data, I would assume. In the mid-90s, there was this thing called SETI at Home, where to help SETI, you could actually download this program, and then when your computer wasn't doing other things, it would pour over all this data, right? Because one of the huge challenges is you collect all this information, but then you have to analyze it. So it'd be this little program so that you could sort of loan your computer and its processing power to help SETI. They don't currently do this anymore, SETI at Home, but it was really popular for a few years in the mid to late 90s. So we've talked about listening for messages, but what about sending messages out into space? All right. Now, there's two examples of that I want to show you. Sending, that is not just sending like a plaque, but sending signals out into space. And so there's two examples I want to show you. One is what we might call like passive messages, okay? And the other is actively sending a signal. So passive message, I'm going to show you an illustration. This is from the very opening of a movie called Contact. It's actually a movie based on a book by Carl Sagan. But the very opening illustrates the signals we are sending out that could in principle be detected by alien civilizations. And those signals are not intentional, right? We are sending television signals all around us. In this room, there's TV radio waves flying all around. There's radio broadcast all around. And all of that not only is flying around this room, but it's also flying out into space. And as we learned before, when you look in space, you're looking back in time, right? Because light takes time to travel to you. And so those signals are traveling out into space, and it might take them 20 years, 30 years to get to another star. So a nearby star, if it was looking and trying to detect radio signals from Earth, might be just now getting television signals from 20 or 30 years ago. And if it's 50 years ago, they might be just now getting the very first broadcasts of I Love Lucy. All right, it's kind of an amazing thought. But so they would be observing us, seeing what we have sent out, and it would be from the very first broadcast. So this illustrates that in a really interesting way. What we're going to start with is a close-up shot. This is the opening sequence of Contact, this movie. We're going to start with this close-up shot of Earth and all the noise, all of the messages and signals going around our planet. And as we zoom out, we're going to be zooming back in time. So listen to the audio and notice how the signals that are reaching these places, as you zoom out, the signal that's reached that point has been further back in time. All right, so take a look and a listen. So notice there was just one small step for man, one giant leap for mankind. So that's the Apollo landing in 1969. So we're zooming out to where that signal has now just got to this place, right? We can keep going out further and further. Martin Luther King. There's the Twilight Zone. Notice now there's fewer and fewer. It's getting quieter and quieter. Lone Ranger, some of the earliest television. This is the radio broadcast from Pearl Harbor. And the very first radio transmissions. And eventually it just kind of fades into silence, right? Because there's no radio or television signals leaking out into space. So in some ways, whether we like it or not, we've already been sending signals out into space that could be detected. Now, whether those signals are strong enough that someone at a different star could actually see them is pretty unlikely. But the point is that we are sending unintentionally messages outward. Now, there's one really striking example of a very intentional message that was sent. And again, this goes back to Frank Drake. So in 1974, Drake, along with some other scientists, assembled a very specific interstellar radio message. So the thought was that we won't just be listeners, we will be, communicators. We will send the signal out. And so what they did is they crafted a message in binary. So like basically flashes of radio light, on, off, on, off, on, off. Sending a visual image is what they sent. And they used this radio dish, which is the largest single dish radio telescope in the world. It's in Arecibo, Puerto Rico. It's kind of built into this huge ravine. All right, it's enormous. It's also, you see it in the movie Contact. and they beamed this message out, and they beamed it towards this globular cluster M13, which has over 100,000 stars. So the thought is that, you know, if any of these stars have planets around them, there could be tons and tons of planets. So by sending it directed at this cluster, the thought was that they could reach maybe one intelligent civilization, maybe more than one, by focusing on a place where there were so many stars all concentrated together. But the message, just like the golden record, it's interesting to kind of look at what message they put together. This is what the message looks like if you were to kind of color code it. But again, it's just blocks of black and white, right? And it consisted of several parts. It walks through here what these are. So at the top, we have the numbers from 1 to 10. Okay, numbers from 1 to 10. And I can't really decipher this, so they'd have to be pretty intelligent civilization to figure it out. After that, what is this purple part? That is the atomic numbers of the elements hydrogen, carbon, oxygen, phosphorus, which make up DNA. Okay, that's the purple section, apparently. And then in green are the formulas for sugars and the bases in the nucleotides. So again, of talking about DNA. And then you see the graphic of the human figure in red, and then the blue is the double helix of DNA. So there's a lot of emphasis on DNA in this message. And then a graphic of the solar system in yellow. So this is meant to show the sun, Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, Pluto. And then a graphic of the Arecibo radio telescope. One thing that's worth noting, so here's this amazing message they put together, right? One thing that's worth noting is that this M13, right, is like 25,000 light years away. So this signal, even though it was sent 20 years ago, is going to take, even though it's traveling at the speed of light, is going to take an enormous amount of time to reach those stars. So even if an intelligent civilization detected that signal, right, and then they were to sort of respond like, "Hello, we hear you," that would be 50,000 years from now. It's incomprehensible, right? I mean, it almost doesn't even make sense. But nonetheless, it's an interesting illustration, I think it's fair to say, of messages that could be constructed to try to communicate intelligence, right? Like, it's fascinating to think, if you wanted to try to communicate with an unknown intelligent civilization, like, "Hello, we're here and we're intelligent," like, how would you do that? One other interesting example here on the Arecibo message, it says, like, because we have to choose a frequency that we want to transmit at. So, like, just like we don't know what frequency to listen to, which frequency would we want to transmit at? And it said here that it sent out this many bits, so 1,679 digital bytes, like, you know, or bits, you know, binary bits, and at a frequency of 2,380 megahertz, modulated by shifting the frequency by 10 hertz with a power of 1,000 kilowatts. And it says the cardinality, like the reason they chose these numbers, 1,679 digits or bits, you know, binary, was because it's a semi-prime number. It's the product of two prime numbers. And so the thought is that this whole picture is 23 across and 73 down. So prime numbers is a recurring theme as something which only an intelligent civilization would understand, the idea of a prime number, a number that can only be divided by itself and 1. All right, so very interesting and challenging ideas, sending and receiving messages from space. There's tons that could be read about it, but hopefully you found this to be at least an interesting introduction. All right, I'll see you next time.